Now, formation of shear fractures. We've got a normal stress. Sigma 1 is our big normal stress, normal being perpendicular, and a perpendicular to the confining pressure, our sigma 3, much lesser than sigma 1. The rock is going to start to fracture about 30 degrees from the perpendicular to sigma 1. So, that upper surface that we're pushing down on, if we drop down 30 degrees from that surface, or come 60 degrees from parallel to sigma 1, so we're pushing straight down, come up 60 degrees from that straight down, it's the same angle. That's approximately the angle the crack's going to form. And this will happen as long as sigma 1 is greater than sigma 2 and 3, and especially if sigma 2 and 3 are equal to each other. The fracture will not slide if this happens, if 2 and 3 are precisely equal. But the crack can grow if the shear stresses are growing, then we'll get displacement. As soon as we have displacement, it's a fault. Might be a microfault, might be a normal large fault. But if there's displacement, instead of just a crack, it's a fault. Now, shear mode cracks cannot grow in their own plane. They bend and curve and change a little bit. Showed you this before, how it fractures, but you notice that crack isn't perfectly straight, and then as movement happens, it's going to be grinding, and it's a dirty, nasty thing. It's kind of like the difference between getting a paper cut and getting road rash. One is a clean, a tension crack is a very clean crack, versus these shear fractures are very uneven, nasty fractures. Now, predicting this brittle deformation. Can we predict it? Is there a regular pattern that we can see? Well, fortunately for engineers especially, the answer is yes. Absolutely, it's predictable, it's possible to calculate it, and that's how we can figure out how strong the bridge is, what how thick we need things, what we need to build it out of to support this much weight, and so forth and so on. Tensile cracking criteria. This is what we use to predict the stress conditions that will make the rock break, that'll make the cracks grow. Now, this is based on the assumption that macroscopic cracks, big ones, big enough to see, grow from pre-existing flaws, from those Griffith cracks. The rest of the discussion of that section of the chapter, dealing with predicting, is the rock going to break? Is it not going to break? That's in lab. That's dealing with Moore circles. So that's the lab that you've started. And then we continue later in the next lab as well. Frictional sliding. This one is important, and a couple of key things. You notice these two gray blocks here. One of them is taller, one of them is wider and thinner, much more contact with that inclined plane on that thin one. But they're the same mass, the same weight. That's why these force arrows are the same length. because they're the same force, they have the exact same amount of friction. They're going to slide or not slide at exactly the same moment. So it's not the contact surface area that's important, it's the force. The movement on a surface that takes place when shear stress parallel to the surface exceeds the frictional resistance to sliding. So, this straight down arrow, F, is force due to gravity pulling the block straight down. Part of that, if you break it apart, if you're familiar in physics, breaking down the vectors into the two perpendicular components, this is the component of that gravity vector that is perpendicular or normal to my inclined plane here. There will also be a small arrow here that is parallel to the inclined plane. That's the shear portion. That is the shear stress parallel to the surface. And then friction would be pointing backwards up the inclined plane, resisting that force trying to get it to slide. As soon as this shear stress parallel exceeds the friction, so my arrow pointing down the plane is bigger than my arrow pointing up the plane, it starts sliding. That friction arrow is completely dependent on this force normal arrow and the two materials. A rubber block on a rubber block has greater friction than an ice block on an ice block. Friction can be divided into two categories. Static friction. It's the friction between two things that are touching and not moving relative to each other. So my computer is sitting on my desk, it's not sliding around, so there's static friction between my computer and my desk. Dynamic friction, also called kinetic friction, is the friction between two objects moving relative to each other. So an ice skater gliding along, there's dynamic friction between their ice skate blade and the ice. Or if you like to go and go drifting in your car, as soon as you start sliding and skidding, there's dynamic friction between your tire and the road. Somebody pushes my computer and it slides across the desk, there's dynamic friction. And then there's a lot of friction between me and the person who pushed my computer. But that's different. Sorry. Now, friction happens because no surface is perfectly smooth. Not even a piece of glass or a polished diamond or anything. No surface is smooth. There are imperfections in that surface called asperities. These asperities mean you have to take into account real contact area. Now, what I mean is, this is like crazy zoomed in, but two pieces of glass touching each other, and the surfaces are not smooth. They're bumpy. And those bumps are touching across each other, not lining up perfectly, and in some places it is touching, and in other places there's gaps or voids between them. If we push down really hard, compressing them closer together, it goes from being like this, where the asperity is digging in a little bit, to being like this, where it's digging in a lot. That's why more normal force increases the friction. The little image on the left here, it would take a little bit of side force to get that to kind of snap off the tip or jump out of its groove. The one on the right, it would take a lot of sideways force. It's dug in much deeper. It would be much harder to get it to slide. So anywhere, these little dark lines where they're digging into the opposite surface, they're the real contact area. They're like these dark spots. Whereas this light blue is the apparent contact area. That's, the surface of, the whole surface of my piece of glass. A very strange shaped piece of glass, but hey. You can see that the real contact area is a small component of that apparent contact area. Now, what out in the real world is going to affect fractures and failure and movement along the fractures? Well, fluids. Fluids create pore pressure, they help the cracks grow, and they lubricate things. So if a rock is permeable, water can flow in and out. There's hydrostatic pressure. Basically, the pressure of that fluid is the density of the fluid times gravity times the height of the fluid column. And that gives us hydrostatic pressure at any specific depth. The pore pressure is exerted by the fluid in the pore, pushing outwards, growing your cracks. Lithostatic pressure, calculated the same way but using the density of rock, is when the pressure approaches the weight of the overlying column. Occasionally, the pressure of the fluid is higher than the pressure of the overlaying rock's weight. It's higher than the lithostatic pressure, and this is only going to occur when there's a factor other than hydrostatic pressure increasing that pore pressure. Water is virtually never more dense than rock. Rare exceptions like pumice, but that's because the pumice is largely airspace. The way you can have pore pressure of the fluid pressure in the pores be higher than the lithostatic pressure is when it's trapped, and then you start raising the temperature. As you heat it, the fluid starts expanding, overpressurizing the system. Now, another important factor is dimension. Large rocks are going to have more Griffith cracks. There's more rock, therefore there are more imperfections. Very logical, but very important. The larger the rock, the more micro cracks, therefore the easier it is to break it. Again, seems counterintuitive. For us, like if we've got a little hammer, it's easier for us to break a small rock than it is to break a boulder. But when you're dealing with huge stresses, if you have a very large unfractured rock, that will fracture more easily than if it already had some fractures and you're looking at individual pieces of it. And so then you get things with folds and fractures and all kinds of cool stuff.